Let's start to talk briefly about one of my favourite areas of the IB Maths course, complex numbers. Now, admittedly, they can be one of the more scarier topics in the course because they're pretty novel when we come across them in IB Maths. But not to worry, I have a plan to get through this together, and maybe I can even convince you that complex numbers harbour their own sort of beauty. So first we'll be talking about what I is, and what an imaginary number is. And then we'll be looking at complex numbers and dealing with them algebraically. Finally, we'll look into more what it actually means geometrically to multiply complex numbers using the polar form. So then, what is I? You may have heard it referred to as the square root of -1, which is true in a sense, but also the whole concept of taking the square root of a negative number seems bizarre, right? Because multiplying either a positive number by a positive number or a negative number by a negative number will always result in a positive number. Taking the square root of a negative number just doesn't seem like it's a valid thing to do. A subtly different way is to describe I as the solution to the equation x squared equals -1. Now, why this became a question that mathematicians even wanted to ask is a really interesting story that I can't get too much into now. But what this way of formatting it does suggest we do is to treat I as some unknown, maybe even unknowable variable. Actually, we do know something about I, which that I multiplied by itself is a negative, which means that it cannot be a real number. It exists as its own completely different thing that we'll call an imaginary number. There are other imaginary numbers too, but they're all just some real number multiple of I. Now, you may be thinking, well, if it's not a real number, then it doesn't actually exist, right? And so what's the point? Well, we'll get to the latter part later, but I'd argue that imaginary numbers are just as much real as real numbers, insofar as they're all completely man-made concepts that are absolutely crucial in allowing us to calculate things in the world to solve problems. Negative numbers and fractions are just as man-made in that you can't have a negative of a thing. And in fact, not that long ago, there were humans that held negative numbers in the same disgust with which you're probably now thinking of imaginary numbers. But all three do exist in that we need them to solve problems that we have in the world, such as debt, land distribution, or sound analysis. So what does this all mean for complex numbers? Well, a complex number is made up of a real number and an imaginary number. As such, we can write a complex number as a plus bi. Like how we commonly use x and y for real numbers, the conventionally used variables for complex numbers are z and w. Now, the normal rules of maths still apply, so we can add complex numbers by treating I as its own weird variable and collecting like terms. We can say that adding 2 to the imaginary number I is just the complex number 2 plus I, and then 2 plus I minus the complex number 3 plus 6i is 2 minus 3 plus I minus 6i, or -1 minus 5i. It might be useful here to think of a number line. Adding 3 is just like moving 3 places along the number line or sliding the number line until 0 is at 3. If we do that, then 2 is now at where 5 used to be, so we know that 2 plus 3 equals 5. Now, the real and imaginary parts of a complex number don't really directly interact with each other, so we can extend the number line by adding a perpendicular axis for imaginary numbers to move in. This is called the complex plane, or sometimes an Argand diagram. Just like we can add and subtract real numbers by sliding forwards and backwards in the real number line, we can add complex numbers by sliding through 2 dimensions. It's important to understand that complex numbers are just points on the complex plane, the same way that real numbers are points on the real number line. But you will often see complex numbers drawn as lines to make it clearer to see what's happening. So to take 5 plus 3i minus 6 minus 2i, we start at the origin and go along 5 in the real axis and up 3 in the imaginary axis. Then, because we're subtracting, we go back 6 and up 2 to land on the point minus 1 plus 5i. In this sense, complex numbers are pretty similar to vectors, although the big difference between vectors and complex numbers is in multiplication. As math rules still apply, we can try to solve this algebraically. So let's treat I as an unknown and expand the brackets a plus bi, c plus di, with one caveat. We know that I squared equals minus 1, so we can change that term to a subtraction. Collecting like terms, we're left with ac minus bd plus ad plus bci. This works as a result, albeit a slightly clunky and unintuitive one. So to recap what we've done so far, we now know what I is and how imaginary numbers relate to complex numbers, and we can do all our favourite basic operations on them, which is pretty cool, considering 5 minutes ago we didn't even know what complex numbers were. But I think there's a better way to think about multiplying complex numbers, and it comes slightly later on in the course, but I want to talk about it now because this finding is so useful that it gets to the very point of what complex numbers are, and it gives you a glimpse as to why they're so useful. Honestly, thinking about complex numbers in this way has unlocked so much of the questions in the IB Maths course for me and all of the IB past papers I've done, so I think it's well worth to always have this in mind when dealing with them. If we think back to the complex plane, it's pretty neat that we now have a place to describe complex numbers and add them as such. But it's not ordered in the same way that the real numbers are, where there's a clear concept of size. So the question is, what does it mean for a complex number to have size? 3 is bigger than 2, but is 3 bigger than 2 plus I? Well, we can say that for any complex number point on the complex plane, it's always some distance away from the origin, and we can call that distance the magnitude, which is often denoted as r or z in a modulus. We can work out the magnitude with help from our old friend Pythagoras. If z equals a plus bi, then r equals the square root of a squared plus b squared, because it's just the hypotenuse of that right-angled triangle. Another thing that we can infer from the complex plane is the angle that it makes with the x-axis at the origin. This is called the argument of a complex number, and we'll call it theta. From GCSE trigonometry, we can say that theta is equal to the arctangent of b over a. Now, taking the modulus and the argument together makes something called the polar form, which we'll look at eventually in a lot more detail. But for now, let's just try to work out a and b if we already know r and theta. We could try solving these as simultaneous equations, but actually we can just use SOHCAHTOA. Cos theta is a over r, so a equals r cos theta, and similarly b equals r sine theta. If we were to substitute a and b for r and theta, and then factor out the r, we get r cos theta plus I sine theta. Now something really cool happens when we multiply this by another complex number with a magnitude of say s and an argument of say phi. If we regroup r and s together and then expand the two brackets, we get this mess. However, if we were to rearrange and remember that I squared equals minus 1, then we can actually use the compound angle trigonomic identities to get this. So why did I bother showing you that? Well, from here it's pretty easy to see that the new modulus is just the first two multiplied together, whereas the arguments have been added together to get the new argument. Take a minute to internalize how awesome this is. It means we have a completely new way of thinking about complex numbers. We can think of multiplying real numbers as stretching the number line, so that everything is 3 times 5 is just 3 stretched 5 times further away, which you can do in your head as 15. But with some practice, you can also do this in your head. 1 plus I and minus 1 plus I both have a magnitude of root 2, and they have arguments of 45 degrees and 135 degrees respectively. To multiply minus 1 plus I by 1 plus I, All we need to do is stretch it by multiplying the magnitudes and then rotate it an extra 45 degrees and land on -2. Check this out algebraically at home to see if it works out. This is the key takeaway. What it means for a real number to be multiplied is for it to stretch, and what it means to multiply by a complex number is to stretch it and rotate. They're like little scalable mathematical rotating machines. This is what makes them so useful in modelling things that are circular.